So now what we're doing is the same thing, but we're titrating a weak base with a strong acid. And it's the same shape curve, except it would start out at a high pH and eventually work its way down to a low pH. As with the last type, weak acid, we saw the equivalence point pH a little bit basic. We're going to see the equivalence point pH be a little bit acidic, because the only substance that will be left when we have when we reach the equivalence point will be the conjugate acid this time. So the problem here is we're titrating 30 milliliters of 0.1 molar ammonia, NH3, with 0.150 molar HCl. And so if I look, this is a little bit stronger of an acid, right? So my equivalence point isn't going to be 30. My equivalence point is when the number of moles of acid and base would be the same. If you do a, molarity times volume equals molarity times volume, that would tell you when the number of moles would be the same. And that's going to wind up being right at 20 milliliters. So our first type of a calculation is when nothing has been added, no titrant has been added, so all we have is the weak base. All we have is NH3. And of course, it will react with water. It will grab a hydrogen off of water, leaving behind the hydroxide ion, which is why the pH is going to be above 7. The concentration is 0.100 minus X plus X plus X, 0.100 X and X. Now the Kb for ammonia is actually the same as the Ka for acetic acid, 1.8 times 10 to negative 5. And that equals X squared over 0.100. Remember, when we solve for X this time, what we're actually solving for is the OH minus. And that comes out to be 0.00134. POH would be the negative log of that, and that's 2.87 for a pH of 11.13. And that makes a lot of sense because we know we would be starting out with a basic pH, a pH that's higher than 7, but not like 13.5, not super basic, because again, it is just a weak base. So now we're added a little bit of titrant. We've added a little bit of the HCl, 10 milliliters worth, and we're going to find out what is the new pH. So the acid that I add is going to react with the ammonia. It's going to produce some ammonium ion, and then I will have a buffer solution, and I will need to then do an ice chart to figure out the pH. So this is BCA, then ICE. This is again half equivalence point, so we are going to notice that the pH is going to be equal to the pH is equal to 14 minus the pKb. I believe that's what it comes out to be. So what do we got here? Ammonia. NH3 reacting with the acid, the H plus, making ammonium, NH4 plus. BCA. Looking at the number of moles using molarity equals moles over liters a whole bunch of times. This comes out to be 0.003 moles, 0.0015, and 0. So all of my strong acid gets used up, and I make some conjugate acid, and I still have some weak base in there. Remember, these are in moles. So now I divide by the new volume to get my new molarity. And I started out with 30 milliliters. I add 10 milliliters. So now I have 40 milliliters, or 0.040 liters. And that comes out to be obviously the same, 0.0375 molarity. And so that's the molarity of both of those. Now we can go and do our ice chart, or we can use Henderson-Hasselbalch When we use Henderson-Hasselbalch, we have to be careful about using the KAs. But what do I got here? Weak base, excuse me, reacting with water, grabbing a hydrogen off of water, leaving behind OH minus. Using an ice chart, because we're doing equilibrium, must be in molarity, 0.0375, 0.0375 minus X, right? KB equals 0.0375 times X over 0.0375, right? We know KB is 1.8 times 10 to the negative fifth, so that means X, which is the concentration of OH minus, equals 1.8 times 10 to the negative 5. POH is equal to 4.74. So the pH is, of course, 14 minus that, 9.26. Okay, so same calculation that we did before with the acid we're doing now with starting with a weak base. Our equivalence point is at 20 milliliters. So this is the same type of calculation, but this time so we're still before the equivalence point. And this is one that is the same calculation that we just did. So if you want to pause and see if you get the right answer, the pH here is going to be 7.66. So pause, do this one out, and then restart the video, see if you get a pH of 7.66. So let's do this one out. One of the questions that I always ask is, what's going on? What is the balanced chemical equation? So when we add that strong acid to our weak base, right, I need to know what's happening. And what is happening is we are forming, that strong acid, that HCl that we add gets completely consumed, and we make NH4+. In a BCA chart, we use moles, right? So we start with 0.003 moles of ammonia, the 19.5 milliliters, change that over to liters, multiply by 0.150, I get 0.002925 moles of acid. Now all of that acid gets consumed. And as it gets consumed, it gets produced as the conjugate acid. And this comes out to be a really small number, 7.5 times 10 to the negative 5. And of course, these are in moles. So my next step is to change all these into molarity, right? We know molarity is moles over liters. So 7.5 times 10 to the negative 5 over, we have 30 milliliters plus 19.5 milliliters, so 49.5 milliliters or 0.0495 liters. This is moles. And what do we get over here? 0.001515 molarity for the ammonia. And then over here, this guy, 0.002925 moles of the conjugate acid divided by the 0.0495 liters turns out to be 0.0590909 molarity. I take these numbers and I put them into an ice chart to find the new pH. The ammonia is acting as a weak base. We figured out that the initial concentration of the ammonia was 0.001515, and the ammonium is 0.05909 minus X plus X plus X. Kb for ammonia is 1.8 times 10 to the negative 5. That equals 0.05909 times X over 0.001515. Now X, which is equal to the OH minus concentration, is equal to 4.61 times 10 to the negative 7, which means the POH is equal to 6.33. So the pH right before the equivalence point is 7.66. It's still a little basic. It's above the basic pH. It's still a little basic, but it's really close to the pH at the equivalence point. The pH at the equivalence point, remember we said, is going to be a little bit acidic because now all we're going to have is the ammonium ion, the weak acid, or the conjugate acid of the weak base. So we'll do the next group of problems in the next video.